when k independent Poisson processes at rates lambda 1 through lambda k are merged, the result is a Poisson process at rate which is equal to the sum of these numbers. We get a Poisson process at rate sum lambda I from 1 to k. Okay, let's call this lambda. To prove this roughly, we can use the Baby-Bernoulli definition of the Poisson process. So consider the first arrivals to the first process at rate lambda 1. So for now, consider k equals 2. For simplicity, it is trivial to extend this to a general k. So suppose the white cross marks represent arrivals to the first process and the yellow represents arrivals to the second process. We record an arrival in the merged process whenever there's an arrival in the first or the second process. Okay, so now how do we know that the resulting process is Poisson? First of all, well, we need to show that this process obeys one of the three definitions of the Poisson process. Let's just use the Baby-Bernoulli definition. Now, as you can see, I have already split time into small delta intervals, so that's what I'm going to use. The probability that there is no arrival to the joint process in some delta interval from n delta to n plus 1 delta is basically the same as the probability that there's no arrival to process 1 and no arrival to process 2. As they are independent, we can multiply these probabilities, and we already know from the Baby-Bernoulli definition of the Poisson process that these probabilities are simply 1 minus lambda 1 delta minus little o of delta, and 1 minus lambda 2 delta minus little o of delta. And when we multiply out, we find that the result is 1 minus lambda 1 plus lambda 2 delta minus little o of delta. So this already is consistent with the Baby-Bernoulli definition of a Poisson process at rate lambda 1 plus lambda 2. How about the probability that there are two arrivals? Well, clearly, that is going to be order small o of delta. And what is the probability that there is an arrival in general? What is the probability that there is an arrival? That is 1 minus the probability that there's no arrival. But from here, it is lambda 1 plus lambda 2 delta plus order delta. And from here, by subtracting the probability that there are two arrivals, we find that the probability that there is one arrival in n delta to n plus 1 delta as basically lambda 1 plus lambda 2 delta plus little o of delta. Okay, so how about independent increments and stationary increments properties? You can easily show that those two properties are inherited from the original processes. So we have roughly argued that the merged process is a Poisson process at rate lambda 1 plus lambda 2. You can see a more precise proof in the textbook or in any textbook that deals with this theorem. And of course, it is very trivial to extend it to general K. So now how about splitting Poisson processes? Let's see, splitting. So this was merging. The next theorem says that, consider n of t, okay, t bigger than 0, being a Poisson process at rate lambda. Okay, and we break this up into two different processes such that every arrival to n of t is sent to process 1, whose arrivals are n1 of t, with probability p, and to the second process, which is the counting process n2 of t, with probability 1 minus p. And these decisions are made independently for each arrival. Okay, the theorem is that when n of t is independently split like this, okay, n1 of t and n2 of t are Poisson processes at rates lambda p and lambda 1 minus p. Okay, so how do we show this? Moreover, though, what is more interesting is these two resulting processes, these two subdivisions of the Poisson processes, are independent of each other. Okay, this may be surprising because if I know the original process, if I'm given n1, then I know n2 exactly. However, if I'm not given the original process, n1 and n2 are independent of each other. So let's do a simple and quick proof for this statement. We are going to use, we are going to write the expression for the probability that n1 of t is m and n2 of t is k. Okay, so there are m arrivals to the first process and k arrivals to the second process, given that there are m plus k arrivals to the joint process, to the original process. Now this is clearly equal to, think of it in the following way. For this, we do not need to talk about the Poisson, for the Poissonness of the process, because we are really asking for the probability of m of the independent trials to have the first choice and k of the trials to have the second choice. So this is like a binomial probability. Among m plus k attempts, what is the probability that m of them go to the first and k of them go to the second? And this has nothing to do with the Poisson process. This is just, m plus k Bernoulli trials. And the probability that m of them go to the first process is given by m choose k, which is m plus k factorial over m factorial k factorial times p to the m, 1 minus p to the k. But on the other hand, this probability is also equal to, by definition of conditional probability, the probability that n1 is m and n2 is k divided by the probability that the probability that n of t is m plus k, by definition of conditional probability. Okay, so then using the equality between this and this, we can express the probability that n1 of t equals m and n2 of t equals k as m plus k factorial over m factorial k factorial p to the m 1 minus p to the k multiplied by this probability, right? The probability that n of t is m plus k. But we already know this because n of t is Poisson at rate lambda. Okay, we already know that that is equal to what? Lambda t to the lambda t to the m plus k e to the minus lambda t over m plus k factorial. So when we multiply out these terms together, we find that this probability is equal to, let me in fact write it out one more time here, m plus k factorial over m factorial k factorial, p to the m, 1 minus p to the k, times lambda t to the m plus k e to the minus lambda over m plus k factorial. Now the m plus k factorials will cancel, and I can reorganize the terms such that this is going to look like lambda p t to the m e to the minus lambda pt over m factorial times lambda 1 minus p t to the k e to the minus lambda 1 minus p t divided by k factorial. Okay, so by inspection, this is the probability that n1 is equal to m, and this is the probability that n2 is k. Although this is not a precise proof, you can make it more precise by thinking a little bit, and if you need to, please take a look at a textbook. So we have shown essentially through this argument that not only that n1 and n2 are Poisson processes at rates lambda p and lambda 1 minus, but they're also independent. We'll use these properties in some examples next.